Hello everyone. It's Friday afternoon on a snow day, and I'm thinking that you guys may be home doing some chemistry and may need some help. So I thought I'd work through one of the problems on the challenging problems designed for fun and intellectual stimulation problem set that I gave you either Wednesday or Thursday, depending on what hour you're in. I want to work through problem number 3. So if you pull this little sheet out, it looks like this. We're going to look at number 3 on that sheet. What we're going to do is react ammonium sulfate and aluminum hydroxide. Ammonium sulfate, aluminum hydroxide. The products of that reaction are going to be ammonium hydroxide and aluminum sulfate. To balance the equation, you're going to need a 3 and a 2 and a 6. Ammonium sulfate is like carbonic acid in that it decomposes immediately when it is formed. So instead of having ammonium hydroxide, it's going to decompose into ammonia and water. We will use that quite a bit as the year proceeds, so I need to know that ammonium hydroxide decomposes like that. The quantities that we're given 50 grams, I believe, of both reactant. Yes, 50 grams. So 50 grams of that and 50 grams of that. And it's actually 50.0 grams, so we'll go ahead and work it as if we had 3 significant figures. The 50 grams of ammonium sulfate, when transferred to moles or converted to moles, is 0.379 moles. I'm assuming by now you guys know how to do the work for that, so I'm not going to show that here in the podcast. We also find that we have 0.64 moles of aluminum hydroxide. So we can see that the limiting reactant is going to be what? Well, we need 3 times as much ammonium sulfate as aluminum hydroxide. We have only 0.379 moles. So the ammonium sulfate is going to be the limiting reactant. The amount of product depends upon the limiting reactant. So we're going to use it to determine the number of moles and then the volume of the product. So we're first going to find the number of moles of the product. So we have 0.379 moles of ammonium sulfate. There's a 6:3 ratio between the ammonia and the ammonium sulfate. So we're going to need twice as much, or we're going to have produced twice as much ammonia as we have ammonium sulfate. Twice as much as ammonium sulfate, or excuse me, twice as much ammonia actually comes out to be 0.758. moles of ammonia. Now there are 2 ways you can go from here to complete the problem. The situation is we're collecting this gas, this ammonia gas, over water, and we're collecting it at 16 psi and 25 degrees C. So 16 psi and 25 C. Well, we can do the ideal gas law approach and use PV equals nRT at this point, or we can use the combined gas law at this point. And I'm going to work it both ways, but the first way that I'm going to do is using the combined gas law. So we're going to write down the number of moles, 0.758 moles of ammonia. We know that there are 22.4 liters per mole. So we end up with, I wrote this down on the paper that I'm looking at on my desk, 17.0 liters of NH3. The catch is that 17 liters is only true, it'll only be 17 liters if the temperature and pressure are at standard conditions. Well, the problem doesn't have the temperature and pressure conditions listed at standard conditions, so we're going to have to find out what this volume would be. What would 17 liters be if it was converted to lab conditions? The 17 liters, once again, is valid at standard because the 22.4 that we used to find its volume is only true at standard. So moles are not affected by temperature and pressure, but volume is. So I took the moles, pretended it was at standard, changed it to use the 22.4 to find out what the volume would be if the temperature and pressure were standard. So now we're going to convert that to what it will be at lab conditions. And I'm going to have to pause here and erase the board so we can continue on. So I'm going to erase some of what I have up here and then continue on with the problem. Alright, I have the board erased. And before we can really do this problem, we're going to have to, this conversion from 17 liters at standard to what it would be at lab conditions, we're going to need to change our PSI over here, 16 PSI into kilopascals. Now I've done this, but real quickly, here's what the work looks like. You've got 16 PSI, and you've got 101.3 kilopascals, kilopascals for every 14.7 PSI. So it's just a dimensional analysis problem, and 110 then is actually the pressure in kilopascals. So making a little V1, V2 chart, V1, V2, P1, P2, T1, T2. V1 is going to be our 17 liters. And once again, we use 22.4 to find this. That's only valid at standard. So we have to change our 17 liters from standard, which is 101.3 and 273 Kelvin, to the lab conditions, which are 298 Kelvin, that was 25 degrees centigrade. And the lab pressure is 110, however it was collected over water. So you have to look at the water vapor pressure table in your problem solver. You'll find that at 25 degrees the water vapor pressure is 3.2 kilopascals. So the actual pressure we're going to need to use is 106.8 kilopascals. My wife just walked down and our dog came with her, so I have my special guest appearance. This is Trudy the dog. Trudy! Come here, Trudy! So this is Trudy the dog, if you'd like to see our dog. She's a big dog. Alright, Trudy's leaving now. Bye, Trudy. Okay, so now we're back to our problem. Get this a little closer again. Alright, so doing the math here, I'll squeeze it in this little box. We had 17 liters. We know that the pressure is going from 101 to 106, so that's an increase in pressure, which should cause the volume to what? Should cause it to decrease. So it would be 101.3 divided by 106.8 would make the 17 get smaller. Then we know that the temperature is going from 273 to 298. Trudy's back. From 273 to 298. So the temperature goes up. If the temperature goes up, the volume is going to go up. So it'll be 298 over 273. I'll take a pause here and work that out. We'll write. So when I work this all out, I get 17.6 liters, which is fairly close to the 17.5 that I had on the answer sheet. And of course the difference is because of the rounding we did in the middle of the problem so that I could demonstrate how to do it. Alright, so that was the combined gas law approach. The ideal gas law approach is a little bit different, but not much. If you remember, the number of moles of gas that we had produced, that is the moles of ammonia, was what? 0.758. So we had 0.758 moles of ammonia. Ultimately, we wanted to find what volume that 0.758 moles would be at lab conditions. So we could write PV equals nRT. I'm going to change back to black marker because it shows up better on the camera. We know that the lab pressure, we just use this conversion we made, is 106.8 kilopascals. We don't know the lab volume. We know the number of moles is 0.758 moles of ammonia. We know the ideal gas constant is 8.31. Since I'm running out of room, I'm going to leave the unit off, but it's 8.31 liter kilopascals per, well, maybe I'll put it on there. Liter kilopascals per mole Kelvin. And the temperature is 298 Kelvin. If you solve that equation for volume, you get 17.6 liters, or something very close to that, because these two answers should agree. So actually the PV equals nRT approach may be a little bit simpler for you. You need to know both approaches. Alright, big picture. What do we do in this problem? We started by looking at our quantities of reactants. Notice that we're given grams here. Started with grams. If you're given quantities that aren't in liters, you're going to most likely first change to moles. In this case, we had to find the limiting reactant. You change grams to moles and find the limiting reactant. These problems will not always be limiting reactant problems. You might have an excess reactant and not have to worry about what's limiting. But anyway, in this case, we needed to change to moles and find the limiting reactant. Then we did a mole ratio, found volume of gas produced, changed it to liters using a 22.4, and then had to use the combined gas law to change from standard to lab. In the ideal gas law approach, we did everything the same at the beginning. Then we found moles of gas, then used PV equals nRT to solve for the volume of the gas at lab conditions. Alright, so that was problem number 3, worked two ways. In problem number 2, you might remember, problem number 2 illustrates the difference in these kinds of problems. In problem number 2, with the zinc and hydrochloric acid, instead of starting with grams up here, you started with the volume. And the volume had to go from lab to standard. So that made all these reverse in problem number 2, from lab to standard. So please look back at that and make sure you understand that difference. If you use the PV equals nRT approach for problem number 2, instead of solving for V, since your first task was to change to moles, you first used PV equals nRT to solve for N, which gave you the moles of hydrogen in problem number 2. Alright, I'm going to stop that podcast for now, see if I can figure out how to make it into a movie again. Hope you have a nice weekend, and keep working these problems. Bye.